Okay, so we've just looked at impulse and momentum, and a nice way to have a go at this is by practicing a question. So there's a really good one on the question sheet from last lesson, and this is question 8. It's online as well. Basically the situation is we've got some ball that's released from a height of 3.2 meters, and it then bounces off the floor and gains a height of 1.8 meters upwards. So they actually give us the mass of the ball and the velocity that it has just before collision with the floor. And we can infer that since it's released from rest, it's going to start off with 0 meters per second, and when it actually reaches its highest point, it'll also come to rest and have 0 meters per second there as well. So the question asks us, first off, what is the impulse, what is the change of momentum that this ball goes through under the collision with the floor? So to do that, we're probably thinking some change in momentum, and therefore some mv minus mu. And actually, since it's the same mass, there's no change in mass, this will just be m brackets v minus u. But to do that, we need this value here, which we don't have. So the first thing we need to do is actually take stock of what we've got and try and calculate this velocity just after the collision. So what do we have? We've got the distance s, which is 1.8 meters in height when it rebounds. The u, velocity just after the collision, is the thing we want. V as well, we know since it's at its highest point will be 0, it'll come to rest. And as always, A is equal to gravity, so minus 9.81. We don't have time, but we've got everything we need. So if we shove these together, we can do a bit of suvat, and we know that V squared is equal to U squared plus 2AS. And what's quite nice is U cancels straight away, since we've got U is equal to 0 here. So we end up with this, and if we do a bit of rearranging, we can see that U squared is going to be minus 2AS. But what I'm going to do is cancel the negative there by putting acceleration equal to minus 9.81. And that will give us that U is equal to the square root of 2 times 9.81 multiplied by the height it gains. And if you put that into your calculator, you should get that the velocity is positive, so upwards 5.9 meters per second, and that's to 2 sig figs. So I'll just write that in there. So that's 5.9. So now we can have a go at calculating our impulse. So we've got that impulse is going to be our m multiplied by the change in velocity. So that's going to be 0.2, and then in brackets the speed afterwards, which is 5.9, minus the speed before, which is minus 8.0. So obviously double negative, they're going to add together, which we expect since it ends up with some positive upwards velocity. And when you put that in, you'll get an impulse of to 3 sig figs, or actually I'll do it to 2.8 newton seconds or kilogram meters per second, whichever you like. So that's positive, it ends up upwards. That's our change in momentum experienced by the ball. The last thing it asks is there a change in energy? So one thing we're always interested in with collisions is it elastic or inelastic? And you'll remember from last week that elastic collisions actually conserve energy, as well as particularly they conserve kinetic energy, whereas inelastic don't. So inelastic have no conservation of kinetic energy. Some of it's actually lost to other things. And straight away, just by inspection, we can see we've started with 8 meters per second and we've ended up with less than 8 over here. So we're probably going to be guessing that it's elastic. Another big giveaway is that it's not bounced up to the same height. if it was an elastic collision, we would expect it to be able to achieve the same height since no energy is lost. But anyway, let's prove this. So our kinetic energy before is going to be equal to half mu squared, and that's going to be half times the mass, 0.2 times minus 8 squared, and that will give us 6.4 joules before. Likewise, our EK afterwards, after the collision, we're going to be using our upwards velocity now, so it's going to be mv squared, and that's a half times the same mass, 0.2, but this time multiplied by 5.9 squared. Banging that into your calculator, that's just 3.5 joules, so we can see there is some EK loss here. It's actually probably lost that into heat, sound with the floor, and actually in doing some work probably compressing the ball itself if it's not perfectly elastic. So the final answer there is that the total change in kinetic energy in this case is going to be the kinetic energy before, or the difference, sorry, between the kinetic energy before and after, and that just gives us 2.9 joules. So we've proved that it's actually, in fact, an inelastic collision. Okay, so that's just a quick run through of one of the questions. Hope that's been really helpful. And what we'll do next is we'll go through some circular motion in the next video. So see you later. Thank you.